In analysing time dilation, that is that moving clocks run slow, there's another paradox that we need to address here, and in order to address that paradox we're going to use the train scenario with Alice and Bob to help put it into context, and then we'll come back and identify what the twins paradox actually is. So once again here we have Alice and Bob, and at the moment there's no relative motion between them, so as their clocks start to tick you'll see that they record the same time and they're synchronized. So if we pause it there you can see both recording 5.87 seconds as we saw in the previous video. If we now have Alice moving past Bob, so we're looking at this from Bob's frame of reference, we can see that as the clocks start to tick, Alice's clock according to Bob ticks much more slowly. So when we pause there we can see that Alice's clock has ticked less than Bob's clock. Again, that's reiterating what we saw in the previous video. What we didn't address in the previous video is Alice's frame of reference. So if we observe what Alice sees, she would see that Bob is moving past her, and so his clock would run slow. So you can see there that Alice's clock has recorded 5.44 seconds and Bob's clock has recorded 3.59 seconds. So both observers are going to record that moving clocks run slow, and so they'll observe that the other's clock is ticking slower than their own, which doesn't seem to make any logical sense. How can they each make an observation that the other clock is running slow? And that's the crux of the twins paradox. So we can see there the paradox is a result of both observers recording the time for the other as passing more slowly. Now the twins paradox is framed in a way that helps to clarify this scenario in a little bit more detail. We're going to imagine that we have two 30-year-old twins. And in this scenario, one of the twins will remain on Earth, while the other twin travels on a rocket, and that journey that this twin is travelling is undertaken at an average speed of 0.8 times the speed of light, and the journey takes them into the far reaches of space and back again. Now, in order to keep this in a bit of context that we've seen before, we're going to stick with the two people here being Bob and Alice. Bit of a plot twist, they're actually twins. And we'll start off looking at Bob's frame of reference. So we'll deal with the Earth here, and to make it a little bit more meaningful, let's place Australia on here as well. Hopefully that looks close enough to being Australia. So Bob is located here, and Alice will be on the rocket that's travelling away from Bob, according to Bob, at the average speed of 0.8 times the speed of light. And as I said, Alice is located on that rocket. So there's the context to start with. Now we need to consider carefully who's recording what time. Imagine that Bob records that the journey takes 50 years from his frame of reference. So that means that he's going to be recording the relativistic time interval, and so Alice will be recording the proper time, so we need to calculate how much time has passed for her. To do that we can use the equation for time dilation, so t is equal to t naught over the square root of 1 minus v squared on c squared. And because we're looking for the proper time interval, we're going to rearrange that to show that t naught is equal to t multiplied by the square root of 1 minus v squared on c squared. So if we substitute into that equation, the relativistic time interval is 50 years. Now because this speed is expressed as a fraction of the speed of light, that value of c squared is going to cancel, so we'll be left with 1 minus 0.8 squared, and that gives us a proper time interval of 30 years. So according to Bob, he records that the trip takes 50 years, but only sees Alice's clock tick 30 years, and so he'll observe that he has aged 50 years, so that now makes him 80, while Alice has only aged 30. And that would make her 60. Now, if we look at this same scenario but from Alice's perspective, and using that same diagram again, with the key difference being that Alice will actually observe that Bob is moving away from her with that speed of 0.8 times the speed of light. So in Alice's frame of reference, it's Bob and the Earth that's moving away, not that she's moving away from the Earth. So now we need to switch this around, given that Alice is the one that's going to be recording the relativistic time interval. Let's imagine in this scenario that she's actually going to record 50 years. And that means that she'll need to calculate how much time she'd expect to see passing for Bob. We've already done that calculation above, and so we can see that Alice in this scenario ages 50 years and is now 80, while Bob has only aged 30 years. So the paradox here is that we have these ages that don't match up. We can't have Alice being 80 and Bob being 60, and then from Bob's perspective, Bob being 80 and Alice being 60. It just doesn't work. We have this situation where these two conclusions just don't fit together. Now, we can resolve this paradox by paying close attention to some of the detail around the scenario. And what you'll notice is that we don't actually have two inertial frames of reference. And that means that we can actually identify who is moving. And we can do that by noting that for there to be relative motion, so that means that in order for Alice to measure a relative speed of Bob, and for Bob to record a relative speed for Alice, one of them must have undergone an acceleration. And it's fairly obvious in this case, if we've got Alice being on a rocket, that she's the one that's going to have experienced accelerations. So in treating this scenario as though it's two inertial frames of reference, it's actually misleading because there is a period of acceleration where special relativity won't apply. Now, in this scenario, we identified that Bob remains stationary on Earth, so that means that he's not undergoing any accelerations. And Alice will have to accelerate and decelerate in order to complete her journey. And so as a result, Alice is the one that's actually moving here, and so she's the one that will actually age more slowly. So in the details that we saw above, the scenario will actually be that Bob will age more and Alice's clock will be the one that ticks more slowly. So this means that Alice is the one that is the moving clock, and that means that she's going to age less. Her clock will run slow, and we get the resolution to the paradox. Now we know that during the constant velocity motion that Alice will have across her journey, they both will actually observe that the other's clock is running slow. So it's important to note that those two observations are still valid. They can still both observe each other's clocks running more slowly, given that the other would be seen as the moving clock. But it's really the acceleration phase that solves the paradox here. And in order to explain that, we actually need to dip into general relativity. So I'm not going to say too much about it, I'll just briefly explain it here. And that is to say that acceleration causes clocks to run slow, and that's dealing with general relativity, as I said. We won't go into that in any more detail than that simple statement there. And that means that during Alice's acceleration, that's when she'll see Bob age quite significantly. So as Alice accelerates, that's when she'll observe that Bob ages rapidly. So that's the explanation that resolves the twins paradox. And as I said, it basically comes down to the fact that in order to compare two clocks, one of the observers needs to accelerate or decelerate so that they're back in the same frame of reference. And that's how we can tell which of the observers is actually moving.